right, then. Guess I'll get into it. So, yeah, as should probably be clear by now, today we're going to be talking about propellants, which is basically the two fluids we use, two because we're using a liquid bipropellant rocket engine, to power the rocket. Now, as it turns out, the trades and the information about which one you actually pick ends up being like very practical and very easy. So I'm going to focus a lot more on the theoretical stuff again here. And that's not because the theoretical stuff is critically important, but just because it's a really core piece of how a rocket functions. It's probably good to know. And if it was just up to the practical things, I feel like it would miss a little bit of the like, hey, this is why we're doing it. Anyway, let's get started on the core. Here's where we are also for reference. Next up, we're going to start actually designing the feed system thing, which is the first piece of like hard physical design that is going to be happening. So first up, I want to review the 4 parameters we talked about earlier. And if you remember them, think, and if you got them all right, you deserve a pat on the back. If you have no idea, you also deserve a pat on the back because, no, that's corny. I shouldn't have said that. Anyway, first parameter is thrust. So that is how much force the rocket engine is creating. The next one is m dot. And m dot stands for the amount of mass that's flowing through the rocket engine. It's not split up into like, oh, fuel mass or oxidizer mass or anything about that. It's just the amount of stuff in pounds or kilograms that's moving through it. The next one is chamber pressure, and that's pretty self-explanatory. The chamber is the part where the burning happens, and the pressure in the chamber is the pressure in the chamber. And the final one is throat diameter. Now, if you recall, we had those last two, chamber pressure and throat diameter, primarily driving the geometry of the nozzle. And the first two had a little bit more to do with quote unquote performance. However, the key part of this system is that if you constrain any two of these, you can calculate the rest. And not through some like really complicated iterative method, you can largely do it analytically. There is generally one set solution. Also, now that you're hopefully somewhat familiar with these, I'm going to start using the shortened versions of them that you'll see more frequently in textbooks and things, just because that's how it's done in the quote unquote real world, and because that's kind of what I'm used to, and I don't want to be saying things and not have explained them. So the shortenings for these are F instead of thrust, which kind of makes sense. F is a force. M dot is still M dot. The chamber pressure is called PC. That's for pressure chamber. And the throat diameter is called DT, which is diameter of the throat. Okay, so the constraints here, when we talk about two of them being constrained, you can find the other two. I want to make a brief note. That kind of does imply that everything else is set about the engine. You can kind of imagine if I built an engine and put water through it, and I used another engine and I put an m dot of dirt through it, or like weird stuff like that, this equation and like these parameters clearly aren't really going to be able to handle stuff like that. So when I say two are constrained and you can find the other two, we're assuming some certain things. And the one that's most relevant to this presentation is given the same propellants, the same liquids that we're using, or not necessarily liquids, I suppose, but the same fuels that we're using to power our engine. Now, for the purposes of this presentation, we're mostly going to be talking about the mass flow, the m dot, and the thrust, which is now F. So we're going to fix the other two. And effectively what I mean by that is, the way you can think about it is we're talking from now on, assuming the chamber looks the same. So the rocket engine itself is like the same rocket engine. And the question is, how can we change the things that we're putting inside it and moving through it to get us more of the things that we want? So yeah, like I said, these are the two that we're going to be focusing on. Now, if you recall, there's a third one that goes with these two. These two are actually a system of equations, and that kind of makes sense. If it was like a system of 4 equations here between thrust and m dot, you'd need 2 more parameters to define it. You'd need an extra parameter in this list to solve a system of 4 equations. If these two were like directly proportional to each other, they wouldn't be separate parameters, because if you knew one, you knew the other. So there is that third one. And if you remember, that one is the velocity coming out of the engine. And that's an important one, because a way to think about this is the thrust of the engine, which is the big goal, is nothing more than the amount of stuff you put through it times how fast that stuff is going. And for now, we're also going to set m dot. Okay. And that kind of makes sense if we're trying to evaluate propellants. We're going to say, we want to get thrust. That's our goal here. And we have the same amount of whatever it is. We could pick water, we could pick dirt, we could pick some explosive stuff, we could pick anything, but we get the same amount and we're trying to maximize the velocity of it. And that's where the like fire part of the rocket engine goes in, because up until this point, there's nothing about any of those parameters or any of these equations that really specify like, oh, and the combustion temperature is this. That's kind of like not in there. And the place where it comes in, the impact is thrust. The m dot is clearly the same because we know that there's no other reasonable way to evaluate it. And so the impact that combustion has to have versus other things is going to be in that velocity, the exit velocity. And the way to think about it is, or a way I like to think about it, would be if I have the same rocket nozzle and I flow, let's say, 1 kilogram per second of water through it, and it would maybe produce a little thrust, versus if I flow 0.5 kilogram of oxygen and 0.5 kilogram of fuel and I burn them, that's clearly going to like make a ton of pressure. A lot of stuff's going to happen, and it's going to look a lot more like a real rocket engine. And so that's kind of where that comes in, and that's what it affects. And what I'm going to do for the rest of this presentation is kind of discuss what that actual effect is, why it affects the exit velocity that way, and how we can pick ones to strategically gain as much of that higher velocity as possible. But first, I have to add a term. And the next 10 minutes of this presentation are going to be a complete waste of your time because there's no good reason that this is complicated, but it is complicated. And sadly, it's the way that in like the 40s or something, people decided to do rockets. So I need to now explain it. And that is what we actually call the exit velocity. It would be super nice if we just talked about the exit velocity, because like we discussed, it's all tied into efficiency. It fits really nicely into that equation, but instead we don't. And I guess the reason I'd say for that primarily has to do with the fact that it's really, really high. So if I'm comparing my rocket to your rocket, it's kind of difficult to work with really big numbers. And I kind of get that that's like not a great reason, and that's true. Like I totally agree. That's not really a great reason to mess with it. But here's the thought. Okay, exit velocities are really big. Let's work with something a little more manageable. Let's divide it by a constant. This is a secret constant. I'm not going to tell you what it is for now, and there is a reason for that. But the point is, exit velocity is huge. Let's divide it by something, and that will scale it down. So what we get is the thing that we call ISP. What that stands for, or what that means, is specific impulse. That word, you don't really need to know exactly why it means that, but really you can tell if the secret constant is just a constant, if the exit velocity is a velocity, this thing we're going to call ISP is just a scaled down version of exit velocity. It controls the other equations in the same way. Increasing ISP does the same thing as increasing exit velocity. When exit velocity goes up, ISP will always go up a proportional amount. So it's like, it's equivalent to millimeters versus centimeters or something like that. Now, here's the really annoying part. If you are familiar with the term specific from your classes, you might know where it tends to come from, and that's mass or weight. Because for an unknown reason, the constant they chose to divide exit velocity by wasn't something nice like 10 or 12 or 100. It's standard gravity. And that is pretty confusing, and it confused me for a really long time. But what standard gravity is not gravity. Standard gravity is an acceleration, and it is an acceleration that happens to be very similar to gravity at a lot of points on Earth. It's that 9.8, blah, blah, blah meters per second you hear a lot. But again, it has nothing to do with the actual gravity where you are. It's just a constant, which is annoying because it makes it look like, oh, hey, something with ISP has to do with gravity. No, it's just a scalar. And what makes it even more confusing are the units. Now, the exit velocity is going to be in meters per second. G naught, which is what that constant is technically called, is an acceleration, so it's in units of meters per second squared. The meters are going to cancel. The seconds is going to cancel with the seconds squared. And what you're left with is seconds. So suddenly you take something nice and easy to conceptualize, like the speed it comes out, and you get this thing called specific impulse, which is measured in seconds. And to me, that's really confusing. And I'm sorry if I'm like taking a really long time on this. The reason I am is because it really confused me at the start. And I spent way too long not understanding what this is because no one just told me, hey, it's directly proportional to the exit velocity. It's just more convenient. This is sad because it makes no sense, but some things to know about it are that the range you normally see these in, so that you can kind of conceptualize next time you see an ISP, it does make things easier in terms of that. It's a relatively small range. The range of almost all rocket engines you'll see in like actual aerospace are going to be mid 200s to high mid 300s. So about 250 seconds to about 350 seconds. If you built a rocket with 400 seconds of ISP, it would be a stunning achievement. If you built one with like 150, that would be a little sad. Also, fun fact, the Germans actually had it way worse. They were the ones who like started a lot of this rocketry stuff. They did something even dumber, which is they took this and then they took the inverse of it. So if you were comparing the efficiency of your rocket to someone else, you'd say things like, oh yeah, no, how efficient is your rocket? My rocket's efficiency is 0.005 to the negative first second, which is like, I don't know why they did this. Maybe one of you knows or will ever see some reasoning behind any of this. And if you do, please let me know, because it truly doesn't make sense to measure a rocket characteristic, the things that are made to leave Earth, based on a constant that has purely to do with gravity on Earth. Anyway, oh, I skipped past something. Now that we know that, I'm going to give you the real version of this equation, the one you'd actually see in the textbook, and the one we're going to use going forward just because it's the way it's done. And I'm going to take that thing we talked about before, that equation with ISP, and I'm just going to rearrange it slightly algebraically, substitute it for the exit velocity, and you can see we're going to substitute the exit velocity and we're going to replace it with ISP times G naught. And this is sad, like I mentioned, but the point is that it's still proportional. ISP is still proportional to thrust. Exit velocity is still proportional to thrust. This is just the way rocket stuff is. And now that we have this equation, this side's kind of over, and I can go back to talking about that water stuff we mentioned before and put it in a little bit of different terms. So if you imagine these two rockets once more, a rocket with some water flowing through it and a rocket with flammable stuff flowing through it and burning and flying out. You can imagine that the one where things are burning and flying out has much higher velocity. I'm not going to talk about velocity too much anymore. Now what I'm going to say is the rocket with the water flowing through it has a very low ISP. And the rocket with some flammable stuff flowing through it and burning has a very high ISP. So the question is, what are propellants for? And this kind of helps us answer that in terms of, and this equation is going to help us answer that in terms of like where they come in and what the impact of good propellants actually is. Another little brief key thing worth noting is that if you rearrange this equation slightly, or that is if you divide if you divide it out and you solved for ISP, you would come to the conclusion that, again, it's constant, so it's proportional. But the way to think about it is ISP is equal to thrust per m dot. So it's kind of a way to think about it is ISP is a measure of the amount of force you get out per unit mass flow through the engine. Anyway, back to what are good propellants. So given that we have a fixed amount of mdot, a fixed amount of mass flow, the best possible propellants are just an efficient way of splitting that up. So good propellants are some combination of chemicals. Generally, it's two. We're going to be talking about systems with two chemicals that react in a way that causes them to go out of the chamber really, really fast. And now let's look at the practical question. Because turns out there's a really, really excellent chemical process for this, and that's obviously combustion. Or maybe not obviously, but one of the chemical processes which causes this to happen very effectively is combustion. And the way I want to look at that is in terms of, okay, now we kind of understand our chemical process. We're going to use combustion, and we want to maximize this thing called ISP. And let's say we have that fixed mdot, that fixed mass flow through the nozzle. We have 1 kilogram per second of whatever we want flowing through the nozzle. And we want to pick a pair of things where these two chemicals have a really high potential to go fast. And then there's a key second part of this, because you've got two chemicals and you can't just put like 10% of one and 90% of the other. There's obviously some point where it would not do much. You know, if I put 100% of my oxidizer, not super important, wouldn't really do anything aside from just putting water. But there is a scale, and that implies that there's a key maximum point. And we're going to talk a little bit about more now is how you find that max point and what it actually looks like. Also, just a note, in case people are a little bit, in case you've forgotten, since you took 124, all combustion is a reaction with some kind of oxidizer. And what exactly an oxidizer does, you can look up. But the oxidizer, in this case, is often oxygen. And then we have some kind of fuel that gets broken apart and bound to. So propellants describe these two chemicals. Oxidizer is talking about the oxidizer in a combustion reaction, and fuel is talking about the agent that's getting reduced in that reaction. You don't necessarily need to think about it as fire, and perhaps more as just a reaction that happens to release a lot of heat. Anyway, I was just talking about what pair results in the highest ISP and what ratio to mix them at. So let's look at a graph I made of exactly those two things. So first of all, a couple things I do want to clarify about this graph. One, the data here is smoothed. I've smoothed the data to help show you a general trend. And this is data for a specific engine. So you shouldn't take these numbers as like necessarily actually meaningful, but the general trend absolutely exists. So you can see a couple things on this graph. One is specific impulse in seconds, and it's on a scale. And the other one is a mixing ratio. So you can imagine there's also something else that needs to be going on, because if I mix two things on my desk here and I light them on fire, they're not going to go very fast anywhere, regardless of what ratio I mix them in. Versus if I mix them in a really good rocket engine, you know they're going to go really fast. Their ISP is going to be high. So this is a graph for a particular engine. These ISPs might be different in a different engine, depending on how I designed it. However, the trend is always going to be the same. So again, pay a little more attention to the trend here. So on the left, we've got ISP. We talked about that. But on the bottom, we have something that's either called a mass ratio or a mixture ratio and is often shortened to MR. So when I say MR, I'm talking about the ratio of how much massive oxidizer you have to how much massive fuel you have. And that's the question of, okay, we've got this m dot, how are we going to split it up? That's the answer to how you're going to split it up. Now, if you look at any of these individual propellants, or actually specifically we're looking at fuels now, if you look at any of these individual fuels, say take a look at methanol, there's a point where it maximizes the ISP and then it goes down. And the same is true for ethanol here, and the same is true for kerosene. So there is a trend, like I mentioned before. This kind of confirms that there is an optimal point where it exists. Now, here's the key conclusion that I want you to take away for this in terms of practical things. I've seen a lot of these graphs, and I think it's very easy to take a look at this graph and conclude that kerosene is, you know, a relatively substantially better propellant than ethanol or methanol, and that perhaps you should really look into using kerosene. and that it's definitely better because it's got a higher specific impulse. For one thing, if you zoom out on this graph, it starts to look a lot less critical. And we're going to go to this when we talk more about practical stuff, because for a student rocket engine, you can see all these guys are in a range that's realistically very close together. And that already starts to imply, okay, the more important things are going to be what happens practically and not where they are relative to each other on this little ranking. Also, key thing to note about this graph is that we're measuring an inverse, so O over F, and that means that there's a certain amount of distortion. It's not linear. And the way to think about that, it looks kind of like it's very squished on one side and very long on the other one. You might look at this and come to the conclusion, oh, it's generally okay to have a lot of fuel, which is far over to the right, but it's not okay to have a little bit of, but it's not okay to have a lot of nope, other way around. You might come to the conclusion that it's all right to run with a lot of oxidizer, but bad to run with a lot of fuel. And that's not necessarily the case, because if you look from 4 to 8, what you're doing there is you're doubling the fuel. But if you look at from 1 to 0, you're dividing it by infinity. So from 0 to 1, there's like effectively perfect to infinity. And then the range from 1 to 8 is just 1 to 8. So I'm not sure I'm explaining this great, but you can imagine if you wanted to quote unquote linearize this, you would change the scale relative to the graph of 1 over x, and things would look a lot less squished on one side. All right, last important thing to note about this graph. While certain ones aren't ranked significantly higher than others, their peaks are pretty different. In fact, you can see methanol's around 1 and kerosine's around 2. On the whole range of this graph, that doesn't look like much. What that actually means is that you need almost twice as much oxidizer in terms of mass if you decide to run kerosene versus if you try and run methanol. And that consideration ends up having a lot more impact, as you can imagine, on your system, because I'll give you a hint and tell you, we do have a significant number of options in terms of fuel, but oxidizer choices tend to be limited. Anyway, now for the important part. We're going to look at what that peak means, and we're going to look at one specific one. We're going to look at ethanol. The peak for ethanol, the point of maximum ISP, is almost exactly 1.5. What that means is there's 1.5 kilograms of oxygen flowing through for every 1 kilogram of fuel flowing through. And I mean, also in any units of mass you'd like. Let's look at why. Now, we're talking about mixing these propellants in a way that we want them to go as fast as possible. And the assumption that most people, including myself, make looking at that, if you've taken chemistry, is, oh, you want to mix it at the stoichiometric ratio. You want to mix it so that the oxidizer and fuel are balanced perfectly, and they release as much energy as you can possibly get them to release. So let's take a look at that. I'm not going to go through this, but this is the balanced equation for ethanol, which is C2H5OH, and oxygen, combusting and turning into some CO2 and some water. The input is this 1 molecule of ethanol and 3 of oxygen. So it's got, and yeah, so when we're talking about the ratio, we only care about the input. You know, it's oxidizer in over fuel in. So we can kind of ignore the right half of this equation. What's the mass of our oxidizer? Well, it's going to be 96 AMU. And for that 1 ethanol, it's going to be about 46 AMU. And what that comes out to is, in terms of stoichiometry, if you calculate it, you should have almost exactly 2 times the mass of the oxidizer for every unit mass of fuel. But that's not right at all. It's significantly off from that, in the rich direction. Now, why that's the case is not necessarily in the scope of these presentations, but it's something that I'm pretty excited about, and it's something I've found is hard to figure out kind of on your own. It took me a while to get it, and I'm excited that now I understand it. And so if you want to stick around slightly afterwards, if I don't go over. Maybe I'll do it during the time, but I will go a little bit more in depth into the technical reason behind that, because it's a pretty key thing. You know, why don't we mix the propellants at the ratio we were taught in chemistry is the best one to get the most energy out of it? But it is a little bit technical and complicated. So all I want to point out now is that it is not at the stoichiometric ratio. It is fuel rich, and it is significantly fuel rich. And that's almost always true. Some rocket engines don't necessarily follow that, but you do almost always get more ISP, more exit velocity, and therefore more thrust per unit mass if you run fuel rich. Now, that's kind of like the theory in terms of here's a graph, but as it turns out, there are also some really strong practical reasons to run fuel rich. So you can know these and understand these and still kind of have a grasp on it, even if you don't follow through the whole technical things. It turns out it's really, really practical. And there are two main reasons behind that. One, colder temperatures are easier to design for. And I'm talking about the temperature in the chamber. So if you have more fuel stuffed into something, as it turns out, the flame temperature goes way, way, way down. Whereas if you have a ton of oxygen and a little bit of fuel, you get a really hot flame. So great. That's super useful. Also, an oxidizing flame, in addition to being hot, corrodes everything it touches, which is really difficult to make a nozzle for. Something I didn't mention here, but has been important on some rockets, just to give some context, is that, actually, no, I'm sorry, that's not really relevant. I don't want to go on a rant. So that's the practical stuff in terms of what runs fuel rich and what doesn't. Now let's actually move into talking about those real fuels. And the three we're going to talk about are the three I mentioned on that graph before. Why those three? Because those three, kerosene, ethanol, and methanol, have to some extent been used in real rockets. They're very close to what we would think of as rocket fuel, especially kerosene. And they're all readily available enough that you could theoretically get your hands on them. There are all sorts of other exotic fuels, but if you limit it down to stuff you could get in practice, those three, in my opinion, tend to be the ones that drop out pretty quick. All right, first of all, ethanol. Ethanol is identical to drinking alcohol. There are some major benefits to it. One, you can get it, and not only can you get it, but you can get it in 100% concentration. Now, if you know about chemistry, I know about like I know it's an azeotrope and stuff, but you can still actually, interestingly enough, get it in 100% concentration. If you're careful, it won't drop down. It's relatively safe. It's not the safest thing ever. And if you drink too much, it could be bad, but it is safe, especially compared to some of the other things we're going to talk about. And I do want to note, if you ever work around ethanol or with it, please do not drink it. It might seem like, oh, it's the same as drinking alcohol. Let's go do shots of the rocket fuel. However, unless you've got like a pretty solid grasp on the chemistry of how it's distillated and have carefully read the material data sheet, there are impurities which are technically allowed in a lot of high test ethanols, which are used in lab applications and considered extremely pure, even medical grade, that have impurities which can seriously injure you and cause lots of nasty stuff to happen. So don't treat it like drinking alcohol unless you know a lot about the underlying stuff that goes into it. Cool. Also worth noting, I'm kind of limiting this discussion to fuels that we call non-cryogenic here. I just mentioned before that these are the ones that are readily available. That begs the question, okay, what do real rockets use then? Now, the main thing they use are really, really highly flammable gases, but they don't use them as gases because a rocket doesn't have room to take up a ton of gas to space. Instead, they compress them and cool them down enough that they become liquids. And when we cool something that's normally a gas on Earth to a temperature where it becomes a liquid, and this isn't technically the exact definition for it, I'm just saying that because I don't want someone to be like, well, actually, but those are what we generally call cryogenics. If you hear cryogenic, think a super, super cold gas that's become a liquid. Things like methane that comes out of your stove or just pure hydrogen are some cryogenic fuels which have often been used in rockets. All right, next one is methanol. Methanol is a really strong choice for an oxidizer, or methanol is a really strong choice for a fuel and systems where you've got limited oxygen lying around. This is another thing that I'd be willing to go into much, much more depth if you happen to be interested. What I'm going to say for now is it kind of has some extra oxygen in its atom, or sorry, in its molecule already compared to these other ones. So when you burn it, you have a little bit of extra oxygen that's already coming into the system from your fuel that you don't need to spend getting it into the system with the oxidizer. However, it's a lot less efficient in terms of reaction energy to bring in oxygen with your fuel instead of just bringing it all in with the oxidizer. So if you've got basically as much as you want of either one, and you can say, hey, I don't have an issue with oxygen, I can get as much as I need, probably not a great pick, because there's a lot of inefficiency, which comes hand in hand with having to have that extra oxygen in its molecule instead of in the oxidizer you're using. So in addition, it's relatively poisonous. And if you take proper precautions, it's not a huge issue. I don't think it's prohibitive to using it in a rocket engine. However, it's probably more dangerous than most things you'd see in your household. I mean, if you took a shot of drain cleaner, actually, I mean, I don't know, but it's on the level of some of the sketchiest things that people are like, whoa, but for whatever reason, sometimes people treat it a little free and loose because it feels kind of just like rubbing alcohol or drinking alcohol, but it's not. Last one is kerosene. Now, kerosene is what's called a hydrocarbon, or a pure hydrocarbon, which means the only things in it are hydrogen and carbon. You don't get any oxygen baked into the fuel, which is good because, like I mentioned before, having oxygen in the fuel molecule lets you get some extra oxygen if you needed more. But if you didn't, it's just inefficient to rip that oxygen off and then use it again to burn the fuel. So because it doesn't have to do that, it has a higher ISP. But as you might remember from the graph way above, that requires a lot more oxygen. If you remember, I mentioned, oh, look, the methanol has an MR of about 1. That means it's about 1-to-1 in terms of oxygen to fuel, whereas the kerosene had an MR of around 2, which means you need twice as many oxygen, and that's largely... This has to do with what I'll talk about after if you're interested, but it has to some extent to do with the oxygen that's already in some of those alcohols. All right. Anyways, now let's move on to the oxidizers. The oxidizers take a little bit more thought. What we want in a perfect world from an oxidizer is something that's super, super dense. And the reason we want something dense is because if we have a certain amount of pressure and we have a certain hole we want to stick it through, which, spoiler, we have that in a lot of places on the rocket, we want the densest thing possible so we can get the maximum flow through our system. That flow is m dot. And you guys hopefully remember the equation by now, where if you increase m dot, the thrust just goes up too. So the higher m dot, or sorry, the higher density, the easier it is for us to build a system with high m dot. We also want something with high ISP, because that's the second term in that equation. And I showed you a graph before of some fuels with different ISPs, and that was with a specific fixed oxidizer. We can do the same thing in reverse. We can fix the fuel and compare a bunch of different oxidizers. We could also compare pairs in the same graph, but that's just another trait that's important for us to take a look at, though, again, if you recall, these efficiency things aren't quite as important when it comes to relative to the other more practical issues. Also, we want something low risk. Oxidizers are very, very dangerous on a different level than, oh, it's poisonous if you drank it. On a level of it can unexpectedly cause extremely aggressive fires, explosions, unpredictable, any kind of dozens of events that are pretty, freaky if you think about it. So low risk at the end of the day is generally the deciding factor, or in my opinion, really should be for picking your oxidizer. There are two oxidizers that I'm going to be talking about here, because as far as I know, they're the only two oxidizers that are very relevant to building a small liquid rocket engine. There are a lot more options you have, but if you do a little research into them, I think you'll find that there are very, very obvious reasons why they wouldn't work, so I'm not going to cover them here. If you do find one and you're curious about that, or you think I'm wrong, I'd love to hear about it. and I'd love to talk over that with you. And, if you find something good, that would be great, because honestly, solving the good oxidizer problem is, in my opinion, one of the hardest parts. So the first one we're going to talk about is just gaseous oxygen. Makes sense. It's an oxidizer, oxygen. Why not? Now, it's nice and efficient in terms of ISP. If you're imagining how much energy you get out of burning something, pure oxygen seems like a great place to go, but it's a gas, so it's not very dense, and that makes it hard to flow the amount that you need. It also is a little bit flammable and reactive. I'll talk about that in a second, though. Other option is nitrous, which is what they put in the cars to make them go fast. What we do, though, in a rocket is, I'm actually not 100% sure whether nitrous systems in cars use the gaseous nitrous or the liquid nitrous, but for a rocket, what you generally would want to do, as far as I'm aware, I'm not quite as familiar with these systems, but you want to use the liquid. And unlike those cryogenics, nitrous can be compressed not to a crazy amount and become a liquid at room temperature. So you've got a compressed liquid that you can use, and that's really cool. It solves that m dot problem really easily. It's a great way to get a lot of it. And if you know about like the density of gases and liquids, it's going to end up generally about 100 times more dense. You get about 100 times more m dot, regardless of what you're doing. And that's because the chamber pressure is about 150 psi, is my estimation. Or about 100. Yeah, 150 or so. So it ends up being about 100 times as dense. But it has terrible ISP. If you just look at the chemical equation there, you've got 2 nitrogens for every oxygen. Nitrogen's not burning anything. So you have these big inert molecules just hanging around, not contributing much. But like I mentioned before, the important factor is safety. Now, just like I talked about in the fuel, brief note on what real rockets use. Real rockets generally use liquid oxygen because it's like gaseous oxygen, but without the one problem I said was a problem. Not only is it like great at oxidizing and super dense, as it turns out, it in some measures gets safer when it's a liquid. Liquid oxygen doesn't really quite burn. It can very quickly become a gas and burn, but it doesn't burn while it's a liquid, and I believe it tends to be a bit less corrosive, but I could be totally wrong about that. The issues with using it for a student rocket project is it requires a lot of specialized engineering that, in my estimation, is kind of outside the scope of what most students are capable of. If you are, do it and absolutely blow everyone away with the best student rocket ever. But as far as I'm aware, those things kind of tend to be, and where they are done in a student environment, the valves and componentry has to get ordered from someone else at massive cost, as opposed to something a lot less cold where you can work with it yourself. It's also harder to get at. So another point of comparison of these two oxidizers is, again, their ISP. So what I've done here is picked 3 fuels, and they were the 3 fuels we talked about. They were ethanol, methanol, and kerosene, and swept them through different mixture ratios and looked at their ISPs. What you'll note here is that the ISPs aren't that much different. At the peaks, all the nitrous ISPs they're a little bit below the oxygen ISPs, and that's because those extra nitrogens you got to carry around. It's not as high as you'd expect, and that's kind of interesting. Who knows why? Or, I mean, see if you can figure out why. But the key practical factor is you can see the optimum ratio for nitrous. You need 8 units mass of nitrous for every 1 unit mass of fuel for mixing optimally for some of these in certain cases. And the optimal mixing can get more complicated. But for kerosene, at least, which is that top one, you need 8 times as much, versus with oxygen and kerosene, you only need twice as much. Luckily, that kind of evens out on its own, because oxygen is the one where you don't need that much fuel, and it's the very non-dense one that's hard to flow. So kind of a match made in heaven. Nitrous, on the other hand, you need a ton of it, but it's super dense, which already gives you a head start on getting a ton of it anyway. Okay, now that last factor, which is safety. Now, in terms of safety, I'm going to make this somewhat brief. I was going to talk a lot more about safety, but I was thinking And I decided that I don't think I'm really qualified to tell you what's safe and what isn't. It's something I spent most of the work on with my rocket. So it's something I really care about and I really want to transfer the information I have. But at the end of the day, what made me comfortable and confident about safety was talking to people in industry, not just skilled engineers, but skilled engineers who'd worked on exact systems that were very closely comparable. And I don't want to put myself or you in a place where I am anything close to the primary point of authority in terms of what is safe and what isn't. So I'm going to explain some general risks that you're aware of, and I would feel much more comfortable talking about a lot of this stuff on a more one-on-one conversational environment. But in terms of me just putting information on the screen and you interpreting it however you might interpret it, that's not something that I think would be responsible for me to do. That being said, I am going to go into some brief slides on it. Nitrous oxide, the main concern we've got is something called decomposition, which is where nitrous oxide separates into nitrous, so the nitrogens, and oxide, which is the oxygens. And it does that really, really aggressively if you touch it the wrong way. This is a weird thing because it doesn't need any fuel to do that. It just splits off into two separate molecules and releases a lot of heat. In practice, it's kind of hard to get it to do that, but it's somewhat touchy and temperamental and theoretically can cause a ton of heat and a ton of pressure to form really, really, really fast. Also, quick side note, I don't know if any of you are like chemistry people, probably no one's going to care about this, but on the off chance that someone does, and you probably won't totally get what I'm saying, so I'm not trying to like say a bunch of technical words. This is just to anyone who also is super interested in chemistry. I encourage you to check out the reaction kinetics of the decomposition of nitrous. It's a spin forbidden process, and it's like one of the coolest and easiest to see ones ever. It's like the only like simple chemical that's spin forbidden. So that's something I think is super cool. If you're at all interested in that chemical stuff, I can send you some cool papers on it. It turns out it's just really, really awesome and super unique. That's a total aside though. The key point is decomposition risks. The other interesting thing to look at is supercriticality. If you're not familiar with what a supercritical fluid is, the way I would put it is it's where a fluid suddenly becomes incredibly unpredictable, weird stuff happens, and for nitrous, weird stuff kind of starts to mean, okay, it might decompose and bad stuff might happen. And where it becomes supercritical, for most fluids like, I don't know, water or something, it's at insane temperatures and pressures. For nitrous, it's pretty close to the temperature it pressurizes itself to on a hot day. So definitely something you need to be a little bit worried about if you decide to pursue a system that uses this oxidizer. All right. The risks for oxygen are a little more straightforward, a little closer to what you'd expect. And also, to be clear, nitrous has a lot of these risks as well, just not nearly to as an extreme extent. Oxygen is great at burning things. That's why we use it. But it's great at burning things, so it will burn everything. It will burn metal. It will burn plastic, some metals, all plastics. It will burn you. It will burn almost anything you put near it in the right conditions. So you need to be incredibly careful about ignition sources. Also, if you compress it really fast in your system, that's a really great way for it to suddenly start making everything catch on fire. If your system has weird little tortuous paths, that's another great way to make it catch on fire. And I know I'm not offering an excellent explanation for all of this. And again, that's because I don't want to present this as me telling you how to be safe, but rather as, hey, look at some things to worry about, do some more research, and or please talk to me about these things and I can give you like my full, complete understanding of it. But effectively, oxygen can burn almost everything in a really bad way. So yeah, oh, this is what I was saying before about safety. I guess I already said that. So yeah, what I think I can really help you with is if this is something you need for your system, I can help you find people to talk to who will really truly know like whether something is safe or not. Something I spoke about before is like, oh, one major thing I got out of this is like where you can and can't cheat. And safety is something I don't think any student is qualified to do in terms of figuring out where to cheat. In fact, I'd maybe even go so as far that if you've got like, that even if you have some engineer who's really, really excited about it, but doesn't know a ton about that particular system, This might be something where it's honestly best to try as hard as you can to find people who've been directly involved with the exact systems you're talking about. And that's something I'd really love helping you do. I don't know if I'm particularly good or bad at that, but it's something I care strongly about everyone doing. I'm willing to take as much time as it needs to facilitate that because it would make me feel much more happy. Okay. Yeah, so you don't need to make assumptions about safety. It can sometimes feel like, oh man, I just don't know any of this, but I want to build a rocket anyway. And that's a thought I had a lot of times, and that's why I paused my whole process a lot of times. And at the end of the day, what did it for me is finding real people. However, with that safety stuff said, it is important to clarify, you know, people use both of these things all day, every day. And I've done a significant amount of research into trying to find cases of people getting injured and killed, building similar systems. Because I'll be honest, when I was building mine, I was really freaked out about it. But what I found at the end of the day is, as far as I can tell, similar systems to ones you build with either of these guys, it's worth being incredibly exactingly careful, but you should view it as not scary enough that you should quit, but scary enough that you should pay all of the attention in the world. Okay, so summary. My brief note on nitrous oxide. I truly, deeply believe it's safer in almost any situation you can imagine. Sad part is, my personal beliefs don't matter. Not even for my rocket do they matter when it comes to safety stuff. I really believe I understand enough to say nitrous oxide is safer, but I don't know that for certain, and I'm not qualified to make that decision. The thing I like about oxygen is that you can find a lot of objective data about it. For almost any material, you can find, okay, when you compress it, what happens? Okay, when there's particles, what happens? Okay, when it's exposed to heat and oxygen, how hot does it have to get? And find a test with that same material of that same size in that same, I guess, exact same conditions. Whereas nitrous oxide hasn't been used as much and just doesn't have that test data, or if it does, I haven't found it, which is why I personally prefer oxygen. But I'm not telling you oxygen's safer. I'm not telling you nitrous oxide is safer. I'm telling you that you need to do your own work and that I would love to help you with that, but just saying it in a presentation is not the right format. All right, cool. So I know I'm very slightly over right now. Am I? Actually, it's not within the time. I think so. But I'm now, if that's all you cared about, you can hop off. But what I'm going to do now is pick which one of these we're going to use for this system. And it's going to be really easy. And then I'm going to talk a little bit about why exactly that is why they lost World War II, Andy. Why exactly, where did my, so I'm trying to find my Excel where I had the decision matrix share. Okay, can you all see this little Excel thing? Probably. It says participants can now see your application. And first thing we're going to do are the fuels. I promise this is literally going to take like 5 minutes. Let's go. Kerosene. Ethanol. Methanol. And these can go away. So the thing is, these fuels are all just kind of like liquids that you can put through almost the same things and treat in almost the same way. It's a very easy swap. So I could design all of them in CAD pretty easily.
Could you zoom in, Paul?
Oh, sorry about that. Thanks for letting me know.
Thank you.
I should have thought of that. How do you, oh God.
Control scroll.
I thought I tried that. I guess not. Is that better?
Beautiful.
Okay,
beautiful.
Nice. Sorry about that. So in terms of this, you can design these systems in almost exactly the same way. And I'm not trying to like just say that without any justification. They're fuels, they're fluids, they have slightly different boiling points and stuff, but you're just keeping them the same up until the injector. You can kind of treat them very similarly, at least to the extent where system looks the same. You could design it in a very similar way. You could build it in almost the exact same way. In fact, my rocket engine, I put some thought into it, and I think you could use all three of these. It just depends on which one you put in the tank. Do they have the same subsystems as the presentations? Yeah, like I said, sure. Can they hit Mach 1 at the throat? And now that's the key, because I think people building rockets like this kill themselves over the performance in the ISP. And this is why I kind of said at the beginning, like, okay, if I just did this, it wouldn't matter. They all have high enough ISP to power a rocket. And the way you can figure that out for yourself is look up rockets that used them and be like, oh, that's good enough. You saw the performance was very, very close. These can all absolutely hit that. Are they all safe enough for the Prop Lab? Yeah, they're like in terms of safety, except actually, maybe not methanol. You know, I know people have gotten a little weird about methanol in the past, so I'll say no. But either way, what's the key difference between them now? All we have left is cost. Ethanol is easiest to find, and I already have some lying around. So that is the propellant. And that seems kind of like, oh, wait, that sucks. Like, was that really engineering? Is that really all there is to it? And yeah, if anything, I think that's kind of cool. And that implies that, again, the little requirement thing we had lets us get all of those nasty things I just spent all this time telling you about out of the way and realize, wait a second, but we could think about m dot and density forever, but that's not really on the goals for this engine, at least. It only needs to hit Mach 1 at the throat. Doesn't need to have any crazy performance. And effectively, Mach 1 at the throat is like the bare minimum for is there fire happening. These all pass that. And I think it would be relatively easy for you to figure that out too on your own by looking these up in books and things. But again, if those are resources you're not aware of and are interested in, I'd love to help you find them. All right, save. There goes that. And yeah, there are colors. Now I'm going to open the presentation back up. Give me one moment. Did I exit out of it? Yeah, I guess give me like a couple moments because I exited out of the presentation. All right. Oh, God. Why does it do that? This is hilarious. I'm going to put this on YouTube. Everyone's going to make fun of me. You guys already probably make fun of me. You should be if you're not. This is funny. Slideshow. From current slide. How hard was that? Not very hard. And there you go. Now for the easy part. Clearly that was the easy part compared to me switching between 3 tabs. So cool. Now if you want, stick around. Here is my brief rant. And I do think this is important. And I think it's pretty cool. I'm at least excited about it. If you're not sticking around, I have a bunch of sources for specifically all that safety stuff. They're at the bottom of the presentation. If you want to hop on the YouTube video, you'll see it at the end. If you want me to send you this presentation, I will send it. And that's one thing where everything is like relatively carefully cited. None of what I said there is just my opinion. And that's something very important. That's a standard I would hope you all also would have if you talk about any safety stuff. So let's do this. All right. First of all, what happens at stoichiometric ratio when you're burning them in the exact right ratio to release the most amount of energy? That's how I want you to think about this. What the right ratio means is the most possible energy released. So we are releasing a bunch of energy here. But what do we want to do with that energy? We want to make something go fast. That's our goal, not total amount of energy. If there was some magical reaction where you could release the energy and channel it like into heating up one like rock in the chamber or something bizarre like that, it would be completely useless. Energy is not the most important part. And a lot of times we think of energy as, oh, it's basically going to be the speed, but not necessarily. And here's the thing about this reaction. What comes out of it? 2 moles of water. Water is heavy and it's a large molecule. Now, what does that mean in practice? The intuitive way I'm going to have you start thinking about it. And then this way is not a complete explanation. And it is not a complete way to think about it. So I don't want you to really totally think about it like this, but the first like little intuitive step is, well, if we're releasing a certain amount of energy and we're basically, we're conserving momentum, we've got our mass and we've got our velocity, they've got to kind of even out. So you can think of it as, hey, if somehow this was lighter, even if we had less energy, if we had something really light instead of water, we're putting the same amount of energy into it, it would go a lot faster. The momentum would solve out to having a higher velocity. So now let's look at what happens when we go fuel rich. What I'm going to do here is I'm going to double the amount of fuel. We're going to go from, I don't know exactly what the mass ratio is, but I'm going to double the amount of fuel from optimum. So what happens now, 2 hydrogens get added on either side of the equation. And those don't combust. Nothing happens to them. They do not change. You took these molecules of hydrogen, you brought them up to space, and they did not participate in any kind of reaction. They just sat there and then got shot out of the end of the rocket. But if you look at the right side of this equation, on average, the molecule is a lot smaller. On average, again. Also, on average, it's a lot lighter. It has a lower molar mass. We're going to talk about what exactly that ends up meaning now. The interesting part to note is that we did lose something. This reaction still outputs the same amount of energy, but it took more mass to do one of these. The hydrogens don't add or subtract energy either way, but they do add mass to getting 1 unit of this reaction done. So in effect, we're getting a little bit less energy out. But if you just view it in the context of one reaction, the same amount of energy is now getting put into a bunch of molecules that on average are smaller. And that has to do with why they end up going faster. Also, here's the cool part. Like this can seem like very like, oh, theory, a little bit of muddly explanation, but it's like exactly that for real. This is a analysis software that I use to kind of simulate, and this isn't actually like very hard. It's kind of like plug it in and it shoots this out. I simulated a rocket that used liquid oxygen and kerosene, which, by the way, rocket people love to shorten things and compress them together. So when you talk about kerosene and liquid oxygen in a rocket, people call it Kerolox, which I don't know. It sounds like one of those like drugs they try and sell to you if you watch the TV long enough. It's like your grandmother for some like weird arbitrary pain, and then at the end it says it'll kill her and doesn't fix the pain in like the fast words. But here's the interesting thing if you look at this, and I set this rocket up to operate at the optimal ratio. So this is the maximum ISP from this. This is the maximum speed that the propellants are going out. And if this was that stoichiometric ratio, every single hydrogen you brought up to space would be combusting. But it's not. In fact, if you look here at where the hydrogens are when they're coming out, half of them are hooked up to an oxygen, and the other half are just getting shot out of the engine. This isn't like, oh, if we just add some extra fuel that doesn't get burnt, the rocket will be more powerful or something, but it's not efficient. This is like efficiency. We're still talking efficiency. It's more efficient to take half of the fuel in your tank, never burn it, and just shoot it out the end of the rocket, which is really weird to think about. And now we have to get into the slightly more technical side, which is this nasty equation. I'm not going to explain where this comes from because I can't explain where this comes from, but there are some cool resources if you're interested in figuring it out. The derivation is not crazy. It's just like, oh man, okay, weird. However, you see VE. This is the equation for the exit velocity. This is a really important equation. This has to do with all of the this effectively sets the performance of your engine. How much thrust do you get per unit mass? Not just like, oh, efficiency, like is it from like a scale of like 90 to 100? This is like really purely, if this doubles, the rocket makes twice as much thrust. And to go quickly over what some of these terms mean, R prime, or I'm going to start from the left and go to the right. The exit, because there are only a couple of these we care about. Exit velocity, you guys know what that deal is. T0, that's the temperature at which the reaction is occurring. R prime is a constant. Don't worry about it. M is the molar mass. So that's how heavy it is. And we've already talked about the two important ones. And the key place that I think sometimes an incomplete explanation of this gets offered. If we just look at these three things I've mentioned before, T0, which is the temperature of the reaction, R prime, which is a constant, and we've got this M at the bottom. That M is the average molar mass of the exhaust product. And like we talked about, when we go fuel rich, the average exhaust product gets lighter. So often you might think, and this is what I used to think, and this is why I'm talking about this. I used to think, okay, you look at that term. If you increase M, that term's going to get smaller. If you decrease M, that term's going to get bigger. And so it's going to make the whole thing bigger. Awesome. Great. But that's not completely the case. What I want you to think about that first bit of this term, everything I've talked to up there, where that comes from is the amount of energy released from the reaction, the amount of energy released per unit reaction-ish. And an incomplete but all right way to conceptualize that is temperature, that T0. You can imagine that kind of has to do with thermal energy that comes out. And M, we know, has to do with how much of the stuff there is, how light it is. So you can imagine it's kind of like thermal energy per unit mass of the reaction. And if I put it in that perspective, you can imagine, you know, adding extra fuel that doesn't get burned definitely doesn't get you more energy per unit mass. So that term there overall goes down when you get fuel rich. It always goes down when you get fuel rich. So to say because the products are lighter is not a full, complete explanation. Now, the fact that that M goes down saves us, because if all that was happening when we ran fuel rich was that the temperature just went way down, that would make this whole thing a lot smaller. Luckily, the M goes down enough that running fuel rich doesn't ruin everything. But the way to think about it is, okay, medium drop in T, small drop in M, overall small change. What's important is the K over K minus 1, or lambda over lambda minus 1. And what that is K is the ratio of specific heats. Now, I don't know if you know what the ratio of specific heats is. I didn't for a long time. And then I figured out what it actually meant. And I was like, oh, wow, why didn't anyone tell me this? So hopefully some of you don't know, and I'll be able to share that with you. Because it's actually really simple. It's used in like all sorts of stuff and like thermo and things. But all the ratio of specific heat is, all K is it's a measure of the degrees of freedom of a molecule. You're like, wait, well, what is that? Who cares? Degrees of freedom, if you think back to like that kind of ball and spring model of atoms, is how many different ways they have to twist and move. And what this ends up relating to is a different kind of efficiency. Our reaction's releasing a lot of energy. And the energy that ends up going into raising the temperature does nothing for us. When the exhaust is out of the rocket and it's really hot, that was wasted energy that in a perfect world could have got put into the kinetic energy, into the VE. So the question here is, how do the degrees of freedom of an atom relate to kinetic energy and all this stuff? And I think I have a relatively easy way to conceptualize it. And that's, if I take a tennis ball, and it's just one tennis ball, and I put energy into it by kicking it, a lot of the energy is going to go into making the tennis ball go fast and far. A little bit of the energy is going to go into giving it energy relative to itself, is going to go into making it spin around. So you can think of spinning around much like what, hot atoms do, or hot molecules, which is vibrate relative to themselves. So I kick this single tennis ball, and most of the energy has gone into making it speed up, has gone into kinetic energy, but a little bit has also gone into energy relative to itself. Now let's increase the complexity of this molecule. Let's add a degree of freedom. The way we colloquially think of, or not colloquially, the standard way to conceptualize that is I take two tennis balls and I connect them with a spring. So it's called the ball and spring model. So I've got these two tennis balls connected by a spring, and I kick that whole system. It's going to speed up, but a lot of that energy I input into it is going to go into that thing spinning, and now also like wiggling back and forth, and also spinning around its axis. And actually, it's not going to end up going quite as fast. A lot of the energy input is going to get absorbed by it vibrating. Now, if you imagine 50 tennis balls connected to each other with like 100 different springs, even if I kick that 50 times as hard, it's not going to go super fast, but it is going to bounce around a lot. And that is like a bizarrely literal, exact copy paste to what happens with molecules when a reaction puts energy into them. When I talk about how many tennis balls there are, that's just the complexity of the molecule. That's the number of degrees of freedom. And the less the degrees of freedom there are, the more energy ends up going into what we want, which is kinetic energy, velocity, and the less that ends up going into the energy that we don't want, that's thermal energy, them vibrating around. So as it turns out, when something is lighter, when an atom or a molecule is smaller, like if you recall those H2s, that's just two hydrogens together with a nice strong bond compared to water, some weird bonds. And actually, it's not exactly water. In reality, there are a lot more products there. You don't get pure water in an engine, even if you're running it stoic. But those light products have really, really low Ks because they have really, really low degrees of freedom. Wait, is it low or high? Which one makes that thing higher? Somebody else do the math. I don't remember if it makes it go up and down. Somebody's got to be able to figure that out. Is that little thing there? Okay, let's see. If K is 1, then that would be 0. If K is 0.9, it would be, come on. I'm sure you can all do this faster than I can.
But it's funny to watch you do it.
Okay, buddy. Or it's gonna be higher than normal, so it's like
I'm not quite sure.
over. Okay, answer is smaller is better. That makes sense. Okay, so the smaller K is, it's also called lambda, the smaller the ratio of specific heats is, the less degrees of freedom the molecules have. And that term there has a huge impact. Much less than that little, okay, the M decreased slightly. So it does not have to do with how light those products are. It has to do with the degrees of freedom they have. And if you've got a couple of those hydrogens, their K is tiny. And they suck up all this energy and it goes straight into kinetic energy. It goes straight into velocity. The water, it sucks up all that energy and a lot of it ends up going into thermal energy. So the way I think this ends up getting confused is people hear efficiency, and a lot of textbooks sometimes will say, oh, because of the efficiency of the reaction. And something's gotten lost in translation somewhere, because it's not talking about the efficiency of the reaction in terms of like energy per m dot. That's going down. It's talking about the efficiency by which the energy coming out of the reaction gets transferred into kinetic energy. And it's not because the products are lighter. That's a byproduct. That saves us from some losses. It's because the molecules are smaller, they have higher degrees of freedom, and I think that's really cool. It's really like one of these things where from the chemistry up, you can conceptualize from a tiny molecule being added to the fact that in a real rocket engine, it ends up going out faster in the real true world. And yeah, that's the deal with that thing. Hopefully now you know that. If you don't fully get my explanation, I'd be happy to try it again and point you to some resources which explain it well. But that's all I have for you guys here. Thanks for sticking around a little bit longer than I said I would. So yeah.